Hooray! We have reached the end of Chapter 10 on matching queries and indexes. I think Chapter 10 is one of the more extensive chapters in this course, but rightly so, because queries and indexes and matching both, of course, should be at the core of any database systems implementation course. And there is one thing I would like to discuss in this particular video. It's a particular application scenario that comes up quite often. And you will see that many of the aspects that we have talked about with respect to indexes and how they can support particular queries will come up here very neatly in this example context. So let's see what's happening here. What we are maintaining in our database is a table of connection data, say, maybe connections like these. Right, so we can see that there are, well, of a train, probably not, well, flights. Flights are leaving from Mos Eisley Spaceport at 9:51 to Tatooine, at 9:51 to Hoth, and so on. So that would be the Mos Eisley timetable of connections that are available to us. Sometimes there are more than one connection. There's more than one connection at a particular time, maybe even to the same destination. So there is a special ID column that tells these connections apart, so that we can, conveniently browse these connection data. We have built a web interface. So that could be the front end of this particular web application that shows a window that lists all of our connections. Okay, and you can see that this window indeed reflects the contents of the table. But even in this tiny slide-based example, you can see that there is connection data of 4 rows, but only 3 rows are being presented in this web-based UI here. Probably there is dozens or hundreds of connections leaving Mos Eisley today, but of course at any one point we would only show a single page, a brief subset of the rows in our web-based UI. Of course, there would be the possibility to use these earlier and later buttons to navigate this UI, to page through the connection data, but all of you have used such web-based interfaces to databases again and again, probably on a daily basis. I don't have to elaborate on this here. So our goal is to show n rows at a time. Okay, and then of course also to support paging, right? What we do not want to do is to load all of these connection data into the front end of the system. So maybe we are indeed implementing a web app and the web client might not have the opportunity, the space or the resources to load large batches of connection data. So we would rather send queries to the underlying database system and have a query report and return only the next or the correct number of rows that should be displayed in one particular page of your UI. And if you push one of these buttons, like here with our mouse pointer, then the next query will be sent to the database system to request the next page. In this case, the next batch of 3 rows that should be displayed in the UI. So that would be the application scenario, something that should be rather common and is probably in operation on this planet while we speak in a millions of instances. So a really relevant scenario, I would say. Okay, so to support such paging, of course, that would be time-based paging, because let me switch back one slide here. It would be time-based paging because we, of course, want to order the connection data by time and then navigate the connection data by earlier and later times. All right. So to store and then index this connection data, we would probably create a SQL table like this. It would be a 3-column SQL table. The ID would provide the primary key, but the primary ordering criterion would be the timestamp of when our connection leaves. So that would be the when column here. I've put when in double quotes because from the viewpoint of SQL, that would be a keyword or a funny column name otherwise, so the quotes protect that column name. Okay, so that would be the primary ordering criterion, and then other metadata like the destination spaceport. Okay, to support this when-based paging, to support the orderly display of information in our web-based UI, we would create such an index, a connections when ID index, a composite index that uses the when, the timestamp column, as the primary ordering criterion, and to disambiguate entries that share the when, the same when timestamp, we would also include the ID here as the secondary criterion. And then, as we've seen many times in this chapter, this would be the order of rows, or the magnitude of the when and ID values in the rows that you will find in the sequence set of this composite index. So the when column would provide the first ordering criterion. It will be in ascending fashion here. And then we would, inside when groups, we would have ascending ID values. All right. So I think this is business as usual, right? So how could we implement paging now? What would be one implementation of a query that the web app could send to the database server to request the next page of connections? Let me consider two options in this video, two options to implement this particular query. All right, so the first option would use two SQL constructs, the offset and the limit construct. Okay, that would be the query that we will send to the database server. This query refers to two parameters, the page parameter and the n parameter. N is just the number of rows that we would like to show in a page. So 2 slides back, you saw that n would be 3 in this particular example. So that's the number of rows per page. And this would be the current page that we would like to display. So we would probably start with page 0 and then have the opportunity to use the earlier and later buttons to change to page 1, page 2, change back to page 1 again, page 0 again. So this would be the page indicator. All right. Okay, well, we could simply use this particular query to implement this paging, I would say. So of course we would access the connections data. We would of course establish a when order on that, because we want to display and access all this connection data in timely ordered fashion. All right. Then we would use this offset clause to skip most of the rows of the connections table, right? In this ordered arrangement of the connections, and skip to the row with number page times n. So page times n, this is exactly the offset of the first row in page that we would like to display now. All right, so if page is 0, then offset would compute a value of 0 times n, which would be 0, right? So we would start at the very beginning of the connections table. If page is 10, then this would be 10 times n. So we would skip over 10 pages and then start with the first row after that. All right, and then of course we would only deliver n rows, because this is just the size of the page. More data should not be delivered to the web client, because probably it cannot cope with more data. Okay, so this is one implementation of the query, the paging query, and well, it would look like it would lead to an index access like the following. Of course, we would use index access, because this is an order by clause that perfectly fine matches our when, ID composite index. Okay, so we could indeed use a scan along the sequence set of this when, ID index to produce the rows in when order, right? So no need for an external or extra sorting operation. We could just use the index, just as we discussed in the previous video. Now this offset value will grow and grow and grow as we page further down the connection table. So if the offset is 0, then we would just scan n rows at the beginning of our sequence set scan, and that's fine. If page grows, and maybe page is 1 now, we would start our scan at the beginning of the sequence set. We would scan n rows, but that's not sufficient. We need to scan the n next rows too. All right, so this would already scan 2 n rows. And you can probably see the pattern here. The larger page get, the larger the offset get, the larger becomes the portion of the scan that we have to perform only to skip over the rows, and then only in the last n accesses in the sequence set we will produce the rows that are then returned to the application, to the web application, for example. That's a real pity, because as we page further down our connections table, maybe there is many connections, most likely a very busy airport, paging will get slower and slower and slower. Let's see whether we can indeed see that in our implementation of the whole idea on the real system. Okay, so here we go. I've prepared all of this stuff already. This is our rows per page parameter. It has been called the n parameter on the slides for brevity, but well, we would like to have a display of 10 rows in each page of our UI. So let's define that. Okay, and here you can see that I've already prepared the connections table with the schema that we've seen on the slides. This is just a query to fill in some sample data because I couldn't reach the Mos Eisley spaceport organization to provide the real data. All right, and then I created the connections when, ID concatenated index and analyzed the situation. So I'm left with this table setup here. So this is our connections table. Okay, the display is a bit too wide here, but you can see that we've got the primary key index, which is probably not of much importance here because we will always be when based, timestamp based in our queries. And then there's this concatenated index, which will play the major role in this experiment. Okay, so if we now look at the connections data, just so that you get an impression of the data here. Let's see, it's a 3-column table. Okay, the first 10 rows look like this. It will also be the first 10 rows in our sequence set of the connections when, ID index. You see that I've used this order by clause to simulate the sequence of entries in this index's sequence set. So of course there will be ascending IDs here, and then there is the timestamps. So you see that they are apart by 1 minute each, and this is the destination planet. Sorry, just jumbled mess here. Okay, right. So everything is set up for our experiment. So now let's start the paging. We will start our paging at page 0, okay, at the top of the connections table. So let's define the this parameter here. Okay, and that would then be the paging query that we've just proposed on the slide. Right, access the connections table, of course, in the timestamp ordered fashion. Skip over those rows that should not be displayed in the current page. We have skipped over these rows already, okay? And then once we've skipped that far, only produce rows per page, in this case 10 rows per page, to return that to the web client. So let's see how that goes. Okay, worked just fine. And indeed, the system used the index scan on the connections when ID index to implement the ordering here. All right, it indeed delivered only 10. It scanned and delivered only 10 rows. Okay, so the 10, this is just the limit 10 that we've seen here. Actually, the limit 10 is implemented above here, and the limit has communicated the request for 10 rows down to the index scan here. Okay, so I think that looks just like we hoped for. That's perfect. Okay, now let's page down further. Let's page down to page 900 here. So that's actually at the very end of the connections table. I think the connections table has like 10,000 entries or something like this. This is page 900 of 10 rows each, so we are really approaching the end of the connections table here. Quite some browsing in the connection has been going on already. Define the new page parameter, okay, and then come again. Now scan again, and now we will probably see a different index scanning behavior because there's quite the number of rows that we have to skip over now. Okay, this takes a bit longer already. Well, a bit longer, quite a bit longer already. This took like less than 0.1 milliseconds, and we are at 4.5 milliseconds here already. And the cause probably is the index scan. Well, as you can see, that index scan has scanned quite a portion of our underlying table. It has now scanned 9,010 rows, not 10 rows, but 9,010 rows, because we had to skip over 900 times 10, 9,000 rows during our index scan. And only the last 10 rows that we encountered are actually useful rows that we could deliver to the web application. Okay, so we can indeed see the index scanning effort grows and grows and grows while we page down the table, and we can even see that in growing execution times here. That's sad. Okay, so it's a very simple, a very intuitive implementation, but it has some consequences on the index scan based implementation that we are using. Okay, so I would suggest that we go back to the drawing board here and consider a different option of implementing this paging behavior. Option 2, okay? And option 2 is not using offset here. Indeed, we will still use limit, and limit will again implement the behavior of only sending a limited amount of data to the web client, namely n rows or rows per page rows. Okay, but to find the rows that we actually want to return to the web application, we will use a where clause now. Okay, and this is the modified paging query that the web client should use to query the next page of data from the database system. As you can see, we are now using a where clause that performs a comparison of the when and ID entries. These are exactly the entries in our index, so that should be supported by this index just fine, this comparison operator. And we compare these when and ID values with the last when and last ID values that we have seen when we produced the last page of data. Okay, so now it's the task of the web client to display one page of data and report to the database system. The next time when we report the next batch of data, we will report to the database system the last when and also the last ID of the last connection that we displayed in our window. So if this is the window that we were just displaying, and this is the list of connections that we were displaying, then there is one last connection that we displayed on that page. And the when and the ID of that last connection, we will report this as last when and last ID to the database system when we request the next page of data. Okay, so this is what is described here. Okay. Well, this is the information that the database system needs to resume, in a sense, its index scan. So when we delivered data to the web client the last time, we delivered this much of data, only n rows. Next time, we want to deliver the next n rows to the client. So we request from the client the information that this has been the last information that we delivered. Starting from there, we will deliver the next 10 rows. This is exactly what we are implementing in this where predicate. This should be implementable on the side of the web client in trivial fashion. The web client knows about the last row that it displayed, so it can just pass these last when and last ID parameters to the database server on the next query. The index scanning behavior that we will see is, of course, this one. We will only deliver n rows in each of these index scans. We will not have the problem of scanning the sequence set from the beginning all the time. Instead, we will use the B+ tree and navigate the B+ tree using these key values directly to this position, which we can use to then start a scan in the sequence set for just n rows and deliver the next results. Okay, so this looks perfect to me. It's a very lightweight change on the side of the web client, and it has a big impact on the side of the database server, because all of these scans will only deliver n rows. They will find their entry point, the entry point of their scan immediately using this particular predicate, and then perform a sequence set scan for very brief window, very small window of rows of n rows each only. And we should be rewarded by that in the sense that the paging speed should indeed be independent of the page number. Whether we page at the beginning of the connections table or at the end of the connections table, the index scan will only always scan n rows for us. Okay, so let's see whether we can see that behavior in practice also. All right, so to implement this, what we would need is this last when and last ID parameter. So in the very beginning, there would be no last when and no last ID. In the very beginning, we would just set the last when and the last ID to simply the very first connection entry in our connection table. And that's what I'm doing here. You see, I'm looking for the very first, I'm ordering by when and ID and looking for the very first entry in the connections table here. Doing that, and I will save the when and ID value in the last when and the last ID variables. This is what this gset command is doing. So what I'm doing here in the field skills SQL shell would be the task of the web client in a real implementation, but it's good enough for our experimental purposes here. So now we have last when and last ID, and they identify currently the very first entry in the connection table. So we could now use this the paging query, the second option paging query that we discussed on the slide. All right, it would use this particular predicate to resume the index scan in a sense at the row with the last when and the last ID value. Okay, we would have, of course, our timely ordered access. This will trigger the system to use the index, and we will only ever deliver 10 rows per page. And this will also be the scan width of our index scan. So much we hope for, at least. So let's see how this performs. That went quick. All right. And well, you can see it's indeed an index scan that has been performed here. Very nice. And well, we have only scanned 10 rows. So well, this had been at the beginning of the table, and also the first implementation option showed this very advantageous behavior at the beginning of the connection table. So the real difference hopefully shows up when we near the end of the connection table. But it works fine at the beginning of the connection table. Here you can see the indexing condition that resumes the index scan in this case at the very beginning of the connection table. Okay, and of course we deliver only 10 rows. All right, so now let's simulate that we have paged far down into the connection table. Indeed, this query is not a paging query. This query is just a query to extract the connection, the first connection on the very last page. The first connection on the very last page of our connections table. So don't be fooled here. This is not part of our web application. this just simulates that we have paged to the very last page here. Let me run this query. So that would be the first entry, the first connection on the very last page of our connections table. You can see that the ID reports as much. So let's set our last when and last ID to this particular value. So this simulates that we have page to the very beginning, very end of the table already. And now let's fire the normal paging query, the implementation option 2 paging query again, right? Everything as before. Let's run that particular query. And again, oh, that's very fast, although we are at the very end of the table already. And as you can see, the index scan indeed only scanned 10 rows, not 9,000 whatever rows, or almost all of the rows. 10 rows only, because this has been all the information we needed to resume. Well, actually, this is the entire information we needed to resume the index scan at the correct position and to deliver the next 10 rows only. Okay, so that might sound like the a bit more complicated implementation, but I think conceptually it's a much better fit with the index, because we are indeed using the index and its key-based navigation facilities to resume the paging at just the right position for the next display page. All right, so much for this particular use case. It's actually one of the more prominent and more important use cases of database systems that you will see out there to produce the next page of information. Often it's really of no use to just dump the entire table contents or database contents into the lab of the application or even the user. Paging is something that you will see implemented in applications all over and over and over again. Actually, the implementation using offset is regarded as the inferior implementation, and there are some people out there on the internet that are preaching to database developers to please do not use the offset-based method. Use indexes and use index key navigation. So use the where-based method, the option 2 that we have just discussed. This is so important to many people that they even produce beer coasters that say please don't use offset, and they even produced such stickers here to please don't use offset. So people, don't use offset to implement paging. Use where predicates and index support in your applications. All right, so this is the end of chapter 10, and I hope that you enjoyed it. We will now switch gears and talk about other operations during query evaluation, not about predicate evaluation anymore. We will next talk about sorting and grouping. We will then talk about joins, and then we will talk about how everything is being organized and orchestrated in complex plans when we talk about plan evaluation and then also query optimization. So we are nearing the last third of the course. I hope you're still with us and enjoying the ride. I certainly do. Looking forward to chapter 11. See you soon. Bye, folks.